So if you have the system where this is filled with solution that contains a solid A, and we have this sample, and we're going to blend it. So in terms of mass balance, at time 0, so the initial condition is that, so when we multiply the solution, the volume of solution, and the concentration of A in the solution, and if we do that, we'll get a mass of the solute in the entire system in the solution at time equals 0. And because mass is preserved, we will get the same. The mass of the solute in the solution will be equal to the mass of solute in the actually, I'll take that back. And we have some sort of solute in the sample that's getting absorbed in the sample. So the volume of sample times the concentration of A within the sample will be equal to the mass of solute in the sample at time 0. And at equilibrium, the solution volume times concentration of solution plus the volume of sample times the concentration of A in the sample will give us the entire mass of solute in the system, which we can represent it at the V solution times the concentration of solution at time equals 0, because there are no solid present in the sample. So this is just conservation of mass we are looking at. And we can, as we all know, the M infinity is equal to the M solute, the mass of solute in the sample, minus the at the steady state, and minus the mass of solute in the sample at the time equals 0 at the initial condition. So the difference between, or we are seeing how much extra solute has been inside the sample after the reaction has occurred. And MT is the mass of solute in the sample at certain time minus the initial mass of the solute in the sample. And when we represent it as MT over M infinity, what that is really representing is the progression of reaction, how much reaction has occurred. And we can put that on the y-axis, and if you put this square root dt over L squared, and we get a bunch of lines. Kind of similar to this one. This is sorption, but something like that. And we get alpha, theorem value of alpha over shown here. Actually, this is the right one, so same thing, ideal case of fixed diffusion, non-constant boundary layer conditions as the concentration is keep changing outside. So number is representing the percentage of solid taken up by the sheet. So when this is 0, that means none of the solid has been taken up by the sheet. And what it's actually trying to say, so M infinity over the volume of solution times the concentration of a solute in the solvent. So when it's zero, what's happening is that this is like approaching infinity. So what we're saying is the concentration, there's too much solute provided that this is such a big number, and it effectively makes it approach to zero. And on the other hand, when it's like 100 or 100%, that means that the solute 100% of the solute are taken up by the sheet over here, or the sample. So it basically ran out of stuff to absorb in the system. And it makes sense because as the number gets smaller, or the percentage of solid taken up by the sheet gets smaller, we see basically like a little bit of a decrease in angle. And so in the same condition, because we are running out of solute in the system more quickly, and since this is just representing like the progression of how the absorption of solute in the sample, so when they're gonna run out of solid more quickly at 90, or this was practically happening. So they're reaching the maximum amount of absorption quicker. That's what's happening. So that was for sorption case, when it's absorbing stuff. And desorption is just the opposite. So the fraction of the release by the sample, which is defined by the M infinity over volume of sample times the concentration of A in the sample at time 0. And we can represent each sorption and desorption by 1 over, the sorption is 1 over 1 plus V solution over V sample, and desorption is just the opposite, so V sample over V solution. And if we go into example, in a case where there is a spherical shaped pill that has the drug A infused in it, and it's located in this stomach, and we're assuming that the film mass transfer resistance is negligible. In other words, the external boundary layer is negligible, meaning that the external resistance is approaching 0. So what that means is the alpha, which is the internal resistance over external resistance, is infinity. Also, the drug is swept or consumed immediately as soon as they're released, further emphasizing that the external resistance is equal to 0. And this drug is spherical, and initially there are 10 milligrams of drug in the capsule, and we are targeting a 50% release of the drug after 3 hours. And this is the diffusivity given at body temperature, and what is the appropriate size of the capsule, or the radius. And this is a surface evaporation problem. So if we look at this figure 417, so we know that alpha should be infinity, so we use this far left line, and we know at 50% release, that was one of the given condition, which means the progress of the reaction mt over, or sorry, m infinity, or mt over m infinity should be a 0.5. And so if you do that, it's somewhere like 0.1 maybe, something like that. And so that's the value we could have for dt over L squared, or all under square root. And if you solve this out by plugging in the diffusivity value, the time in seconds, and length, which is the radius in our case, we get r equal 0.3 centimeter. And this kind of makes sense because with this parameter, so it's saying that, for example, if you had less time, for example, instead of 3 hours, we needed to release it in like 1 hour, so smaller t. That means in order to maintain same 0.1 r, because this has gotten smaller, r needs to get smaller, and smaller radius drug would indeed release a drug faster in shorter amount of time. Or well, we could also say that diffusivity, if the diffusivity was higher, we wouldn't need to, and the time was same, then d is getting bigger, so this king needs to get bigger to maintain same number. It makes sense. When the diffusivity is higher, the capsule can afford to be bigger to release the same drug at the same rate, or the drug at the same rate. And in terms of the effective alpha value, or we can see that the decreasing number of alpha corresponds to decreasing slope. What it means is that internal alpha is representing the internal resistance over external resistance, right? And the smaller alpha means this bigger external resistance, or the power, the influence of external resistance is higher. And when the external resistance is higher, so even if the drug comes out through their capsule, they have to overcome bigger barrier to actually get released. And so this factor needs to work harder in terms of, or in other words, this factor's influence is decrease. This is about the drug itself, or the geometry of the drug itself, a property of the drug itself, but its influence is lower because of its bottleneck by the external resistance. So its slope, which represents its power or influence, is decreased as the alpha is decreased. Second question is a drying log in a kiln. So we all know that the log needs to be dried and have certain moisture, meet the certain moisture content. So it's just the log in a kiln that's releasing water. And we are assuming that the log is 12.2 meter, with a diameter of 0.3 meter. And the diffusivity of water in the wood is this. And the water has a 5% mole water over air. So that's like the humidity. And how we will solve it? Well, first of all, this is a surface evaporation problem. Oh, sorry, I forgot to skip. So the maximum water content in the log is 0.15. So anywhere in the log cannot exceed the 15% water content. And we can all know that the center of the log, the r equals 0, this has the highest water content, and this cannot exceed 0.15. And in order to solve this, so this is surface evaporation problem because that's what's happening over here. And we need to know the concentration profile. Once we know the concentration profile, so let's say this is R radius, and then this is water contents. And this needs to be smaller than 15%. And it's probably going to show something like that. This is drier on the exterior, where it's facing. Once we know the concentration profile, we can tell what kind of water contents it needs to have on the edge of the radius to satisfy the requirement of 15% requirement.